years ago. And that probably caused, the Sagittarius dwarf, you might have seen picture, is currently disrupting. It's a tiny galaxy of 10 to the 7 solar masses. So most people so far thought, okay, it's a tiny galaxy, what does it do to the Milky Way? Totally irrelevant for a disk of 10 to the 11. Well, this is kind of the revenge of Sagittarius on us, which is now we have to worry about its effect. So it shows actually that galaxies are not island universes. So one of the premises of galactic dynamics is that we take systems in equilibrium, in steady state, and from there, for example, we try to derive the dark matter content, for example, in the solar vicinity. Now we have to drop one of these very strong assumptions, which is that of equilibrium and time independence. And that is tricky, and we're not yet out on how to do this. So for example, one of the first things we thought we should do, and this was before we had seen the data, is we'll make a new measurement of the density of dark matter near the sun, because the data quality will be fantastic. And we're still stuck waiting for that to happen, and you'll see no group has really done this so far. And that's because we have to worry about this. So I think that is one of the...
Life is more complicated.
It's way more complicated. When you have good data, things are not like you thought they would be. Okay, so that is for the disk. So let me try to now move on to the halo. So at the beginning, I tried to convince you that the halo is really a treasure trove. So if you build a halo from mergers of different galaxies, then as shown here, this is from a simulation from the Aquarius collaboration, the Virgo consortium, the Aquarius halos. What you see is the different colors indicate stars from different objects. And so what you see at large radii is that you have features, structures, streams.
What do you mean from different objects?
So the idea is you have different galaxies coming in together. Right. So these are, each color represents a different progenitor galaxy. And so you can see that if you make a map of the sky, that you would expect to find substructure, especially if you look at outer galaxy. But if you look at the inner regions, it's rather well mixed, and it would be difficult to distinguish one from the other. However, like I was saying, stars actually do remember where they come from. So if you take one object and you look at the spatial distribution of the stars, and this is from a simulation, then what you see is that actually the stars don't move randomly through space, but they follow the orbit of the progenitor system. So what you see here, for example, is a group of stars moving in this direction. You see this flow, and they come around, and they produce another stream in this direction. So in fact, from all of the objects that built the Milky Way halo, the prediction was that there would be several hundreds of streams crossing the vicinity of the sun from the different objects that built the halo. So what we're after is looking for these different groups. So we've known already now for more than 10 years that indeed the outer halo shows lots of substructure with the Sagittarius streams, over densities, narrower streams, and so on. But we really didn't know how the inner regions of the galaxy would look like. And what's important about the inner regions is that we think galaxies form inside out. So if you look at the inner regions, you're looking really at what happened at the beginning. And so that's why it's more interesting. So then the question was, how do we find these streams? And like I was showing in this snapshot from a simulation, if you have some stars from an accreted object, then if you're, say, looking around the sun, in a volume around the sun, and you plot the velocities of the stars, so stars moving, say, in the x direction and in the y direction, then you effectively will see two groups of stars, right? So one clump would, for example, be this clump, and then this other clump would be this one, right? So we're plotting two velocities. Now you can take this one step further and look at integrals of motion. So if you think about, a satellite galaxy initially, so all the stars are in the same place, they have similar velocities, so they have similar energies, and they have similar angular momentum, right? Now, if energy and angular momentum were conserved quantities, this would not change in time. So if I actually plot all of the stars here in energy and angular momentum, so angular momentum and energy, then all of the stars fall into a single clump. And so that is for one satellite. If I then have all of the objects that build up the stellar halo, of course I don't have colors, it all looks black and white. If I look at the velocities, then I expect to find different groups corresponding to the different objects. And if I look into energy and angular momentum, each one of the satellites that fell in actually defines a clump in this diagram. And so even if I didn't color code this, if I did it just black and white, the expectation would be that every one of the galaxies that fell in would define a structure in energy and angular momentum space that would be easily identifiable if these were conserved quantities. So that was the basic premise. We thought we have a method. Let's look at the data now. So look at this was actually a prediction from me from the year 2000, so I had to wait 20 years almost to actually check what the data looked like. But it was worthwhile the wait. So,
Especially since it's over.
What did you say?
Especially since it's over.
Yeah, well, I did other things in the meantime, so it was okay. Okay, so what we're after is a sample of halo stars near the sun from the Gaia data. And so what we did to select halo stars, so we just first plotted all of the stars within a kiloparsec from the sun. We plotted the rotational velocity of the stars, and this is Vx squared plus Vy squared. So this combines the radial motion with the vertical motion. And what you see here, this is known as a Tumbre diagram. What you see here is very clearly the disk, the thin disk of our galaxy. So most of the stars, in fact, in this sample are here. But what we would normally call a halo sample would be all of the stars that are beyond kind of this region. So they have very different motions from the disk of about 200 kilometers a second difference. And then what you see is that what is this region here in black would be your halo, and then your halo doesn't really look smooth. What you see here is clearly an overdensity, which follows the shape of, say, the tail of the disk. So actually, a fair fraction of the stars that we thought were in the halo are part of the thick disk of our galaxy. They follow this. They are the tail of this distribution. And then we saw this big overdensity here, and quite a bit of structure there. If you plot the other velocities instead of like this, but you plot rotational velocity against radial motion or vertical motion, then you again see the tail, clearly the tail of the disk. This is the disk. It's asymmetric, like it was asymmetric for the thin disk. We had Hercules here. Now this is the tail of that. So that asymmetry is probably induced by the bar, even at halo-like velocities. And then what we see is, if you look closely, is we see quite a few groups, plus this feature here. So these groups are now highlighted with different colors. And the fact that they have the highest velocities, actually, that you find structures so easily at high velocity, is consistent with the halo being built via mergers. If you look at the energy and angular momentum, then you see a few overdensities very clearly. You see this feature here, and there's an overdensity here. You can also look at other components of the angular momentum, and this structure is that structure there. But this didn't look like the plot I showed you, right, with the many different colors. It looks quite different. So the thing that's most prominent about this is this feature here. So then we decided to inspect it more closely. It's what we call the slightly retrograde blob. What's interesting is, I didn't mention this, but if you look at the Z angular momentum, so this is the angular momentum in the plane around the galactic center, the disk is here. This feature has a mean Lz, which is negative. So it's slightly retrograde. Right? And so at that point, when you see that a fair fraction of your halo is moving in the opposite direction that the majority of the stars in the galaxy, then you think, what's going on? The blob. So this is the blob. And so we looked at this diagram again, and then suddenly I remember I had seen a plot like this in one of my simulations from, actually simulations that a PhD student of mine had carried of the formation of the merging of a heavy satellite with a disk galaxy. And so this is the same velocities. These will be star particles in that simulation. So this is a 5-to-1 mass ratio merger. This would be the disk, and this was the satellite. And so the analogy then made me very suspicious that what we were looking at was really debris from the merger, from a relatively heavy merger that the galaxy had experienced. We can tell from this feature here that we also see in the data that, that the object